Okay, so the recording is in progress now. So I'm switching back to the screen sharing. Okay, can you see my screen?
Yes.
Very good. So this is the FOC module, and we denoted by lambda n the Heisenberg algebra generators. So in particular, the positive lambda kill the high state vector, m being the vacuum, and the negative lambdas they generate the whole space. Yeah, by the way, let me repeat once again that your questions are very much appreciated, and your comments and so on. So if you have anything to say, please do it. Okay, so these are our Heisenberg generators, and we've also identified this F. So can you see the screen?
Yes.
Yep.
Yes.
So we have the bosonic part, which is B, and our B is the normal ring in Z 1, 1x2, so on. So these are infinite number of variables, and Z to the power plus minus 1. And then this B is the direct sum of Bm, m still being an integer, with Bm being Z to the m times polynomials in xi. Well, and then we had the identification, sigma from F to B, by saying that lambda j is d over dxj, j positive, and lambda minus j is jxj, still lambda positive. So this is the identification, and well, the kind of most important for us, most important part of the story is the following. So we had the verging and contracting operators, vi hat, r hat, f to f. So in particular, vi hat acts from fm to fm plus 1, like this. So, and vi star hat vice versa. So the question how to translate vi hat, vi star hat to B. So there's no good answer in this form. So meaning that in principle we have to somehow introduce some extra objects to answer this question, but the object is rather clear. So this is a generating function. So we put x of u to be the sum u to the k vk hat, like this. And so this is just the generating function. So u can be seen as an formal variable, and this is just a formal series with coefficients being operators on f. And similarly with x star of u. And then we translate, instead of translating a single operator to B, we are going to translate the whole generating series. So we say that gamma of U is sigma inverse x of U sigma. So Vi from F to F yes, so Vi hat x from Fm to Fm plus 1. So Daniel, is it your question, or so this is the point? You're asking about this formula, or? Yes, indeed. So that's right. And so the reason is that you somehow verge with Vi, and therefore, so you add one more vector, so the charge is increased by 1. And in the opposite direction, Vi star x from Fm to Fm minus 1. So this is the maps. And now we have gamma of U and gamma star of U. So these are now operators on B. And we would like to have a concrete formula, since B is a very explicit space, so just a polynomial space. So we better have some explicit description. And the explicit description is given by the following theorem. So saying that gamma of U is Z U to the M plus 1, and then X of some JXJ, X minus some J over J minus D over DXJ. So let me check if I wrote it correctly. Yes, I did. So similar for gamma star of U. So please note, for example, remark. So first of all, this gamma of U restricted to Bm. So clearly, gamma of U x from Bm to Bm, well, to be Bm plus 1. So to be precise, to Bm plus 1 U. Yeah, so these are, if you take a vector in Bm, and then you apply the series gamma of U, then you land in the result is a series again in U, and the coefficients are vectors in Bm plus 1, just by the very definition. For example, if you apply, say, gamma of U to the vector Z to the M. So you remember Z to the M is a vector in Bm. And then, so the result would be Z to the M plus 1. That's good. And then you take U to the M plus 1. And then the exponent on the right. So this exponent kills, well, stabilizes Z to the M plus 1. Yes, so all the derivatives kill it, but well, we have 1 in the exponent. And then, so the result is just X U to the J XJ. Let us make a brief check. So let's see how, we take x of u and apply it to m. So recall that z to the m and m are the corresponding vectors, so just identified by sigma. So this is nothing but the sum u to the k vk at overall k to m. And then clearly you converge with m plus 1 and so on. So this is u to m plus 1 times sum k greater or equal than m plus 1 u to the k vk converge m. So in particular, we see that the series starts with u to the m plus 1, as it should be. I mean, here. And also we've got a very explicit description for such vectors as the coefficients if we expand the exponent.
Probably we shouldn't have pool to m plus 1 because we have pool to m plus 1 in the sum.
Good point. Yeah. This is absolutely correct. Like this. So this is the series, and actually why we do care, because so another remark says that the expressions, well, the series gamma of u and similarly gamma star of u are called vertex operators. And these are actually more or less the first examples of vertex operators. Well, so we are going to define more complicated object consisting of many operators, but at least you can see here the flavor. You can feel the flavor of series with coefficients being operators acting somewhere, and so this exponent is somehow very explicit. So the final remark is that in principle you can see that in the theorem, so the product of two exponents, and one of them is a series in u to the negative powers, and another is a series u to the positive powers. So there could have been problems, but if you apply the right exponent to any polynomial, then only finite number of terms survive. So actually the right exponent being applied to any vector produces a finite number of terms. And this is not a series in negative u, in u inverse, but a polynomial in u inverse. And then you are kind of free to no problem to multiply it with a series in u. Okay, so I'm going to move further. So do you have any questions concerning this boson fermion correspondence, these vertex operators, so on?
Yeah, sorry, about what's now written on the board. How do we see that those are like the same expression, that those are related by sigma? Like in B and in F.
What the expressions, you mean what expressions?
Yeah, for gamma of u of z to the power m and x of u of the vector m.
Well, you see, this is it's corollary from the theorem, right? Because m corresponds to
so it's not something obvious, it's
not at all.
It's what follows.
Yeah.
Yeah, then I kind of wanted to ask about like maybe a hint for homework, because I get how to prove that this expression satisfies all those commutation relations we discussed last time. But then it still doesn't prove that it's the exact action of gamma of u on BM. So
maybe somebody can give a comment to the question. So somebody who did send me the homework.
In book,
I
it's
sense
typically written it's unique up to constant.
Maybe somebody can give an argument.
so we had these relations that lambda m and lambda minus m, how it computes with gamma of u. So we can check that these relations determine gamma of u uniquely up to constant. Then we check these relations. That's what you have done already. And then you just need to find this constant, and this is easy. So that's how I done it.
Yeah, I just failed the last step, so probably.
So Jenny, the problem was to compute the commutator or what?
No. So yeah, it's unique up to so a central element, so a constant. But we don't know anything about the action on the on B.
We know. May I say how to?
Sure. Yes.
We know that that in degree m is the same as vacuum, and ну, в общем, тут написана формула, кажется. Вот x от u действует на на вакуумный вектор, как... Ну, короче, у него первый член — это u в степени m без какого-либо коэффициента, вот там u в степени m. Ну, самый старший член.
Yeah, so what you're saying is that x so x of, or rather gamma of u applied to
Z в степени интегрируем.
It starts with z to m plus 1, u to m plus 1, plus something else. Yes?
Yes. And the next terms are less, has highest degree than m plus 1.
Yes.
And this equality is gives us constant, which we need. Вот.
Okay.
Yeah,
So
thanks.
Yeah. So once again, the logic is that if you know how so first of all, since you know the commutator of xj with gamma of u, so this we know. So therefore, it's enough to determine gamma of u applied to z to the m. Yes, because so all other terms are obtained via this commutator. And then in order to understand what is this gamma of u applied to z to the m, we use the commutator gives us the information about gamma of u applied to z to the m up to a constant. And the constant is known by this. So this is the brief outline. Okay, so further questions? Okay, so if not, let's go further. So let's start the, so these were the introductory lectures. So just to understand what's happening. And now let's go to the Vertex greater algebras. So I'm not sure we will be able to get to the definition today. However, we'll define the main objects, the main players. So the first of all, so we consider we'll be working with the objects of the following form: Z1, Zn. So these are series. So maybe even let me write explicitly. So the sum A I1 IN up to Z1 to I1 and to IN, where A I1 IN are elements in the ring R. So ring or algebra. Like this. And so even more, let me be more precise. So here this I 0. So let me be more precise. So we'll be working with, we'll need one more piece of notation. So R of Z. Okay, so let's see how. Yeah, maybe I should start with this. So these are Laurent series. So the sum A I Z I with I greater or equal than sum n. AI sum R. N is an arbitrary integer, so not fixed, but may depend on series. And so in particular, the most important example for us would be R being the endomorphism algebra of some vector space. Okay, so we'll also need notation. Well, maybe we've already seen this, but nevertheless. So R of V. So there's a formal power series. Z. So what else do we need? Maybe that's it. Yeah, and maybe one more remark. So if R is a field, then R of Z is a field as well. Okay, so in order to demonstrate your the object we're going to work with, and also maybe to somehow have something to as an example, let me put it even as a definition because it's going to be very important for us. So we'll consider the following delta series or delta function, so denoted by delta of z minus w. So this is a formal series. So the sum z to the I w to the minus I minus 1. So in other words, this can be written as sum over a plus b minus 1 a w to the b. So this is the the formula. And so why do we care? Because of the following important observation. So lemma says that z minus 1 w times delta z minus w is 0. So can you explain why?
Because because тут, if we multiply the, to z this formal series and or multiply minus w, короче, если мы умножим дельта функцию на z или на минус w, то или на w, то мы получим один и тот же ряд. Вот, и они со знаком минус сократятся. Вот.
So please say in words if you want to discuss this in more details. Okay, so if not, let me make even stronger statement saying that a of z delta of z minus w equals to a of w delta z minus w for any a of z in C of z plus minus 1. Yes, so we take any series and then we multiply it with delta function, and then what we get is still 0. Well, the proof is actually the same. So z to the n delta z minus w equals to w to the n delta of z minus w for any n. And the proof is actually absolutely the same. So this is the reason why it's called delta function. What is a bit less trivial is the following. So let me put it as another lemma. So saying that for any, saying that for any n greater than 0, if you take nth derivative of delta with respect to w, and then you multiply it with z minus w to the n plus 1, then you get z. So is it clear what's written here?
Can you repeat again?
Sure.
The first term, I just can't understand it.
So this is z minus w to the n plus 1. So maybe I should write it more carefully. So we take the difference z minus w to the power n plus 1, and then we multiply it with the nth derivative of the delta function. So there's some comment of Daniel. Yes, exactly. This is the partial derivative with respect to w of the series delta z minus w. So can someone explain why this holds true?
Сейчас. Сейчас, ну...
Maybe by induction and using commutation relation of dw and multiplication by z minus w.
Right, right. So first of all, for n equals 0, we have z minus w delta of z minus w is 0. This is already known. And then for larger n, so we can use the derivative. So by induction, so say if we take z minus w to the n, and then dw n minus 1 delta of z minus w, and then we apply here dw. So we know that this is 0. So from one hand, from the other hand, 0. And from the other hand, this produces, yeah, maybe I should write n plus 1 here. Okay. And then, so if we take the derivative, and it gives us n plus 1.
А если там n plus 1, то мы пока не знаем, что это 0.
We do know, because if even if the power is n, it's 0, and we are taking the larger power. Yeah, so we multiplied 0 by z minus w. Okay.
Ну да.
So this is n plus 1 times z minus 1 to the n. Well, probably times minus 1 to be precise. So which is still 0, and then plus the term we do need. Like this. So that's it. So this is 0 by induction. And we are done. So you see this delta function and its derivatives somehow serve as kernels of the products of the multiplication operator by z minus w to some power. And we can actually make the statement more precise. So let me put forward the following proposition. So let A of dw be some series such that, so if I multiply z minus w to some power n, then we get 0, and this azw is just the sum, say a ij z to the I w to the j, like this. So then a of zw is equal to the sum k from 0 to n minus 1, gk of w, kth derivative with respect to w, the partial derivative of the function delta z minus w. Okay. So so the claim is just that the any solution of this z minus w to the n times a being 0 can be written in such a form. So clearly, yeah, and maybe I should also add that with gk of w uniquely defined. So so clearly the right hand side satisfies well, so the right hand side is killed by multiplication by z minus w to the n, this. Okay, and then so let us consider that delta of so okay, so let us consider the collection of coefficients.
Сейчас, а можно вопрос?
Yes.
Ну, недостаточно, можно просто как-то понять, что вот z минус w, вот умножение на z минус w, оно имеет одномерное ядро, и потом понять, что из этого, значит, если мы n раз его применим, то значит ядро будет ну, не более чем n-мерное, и вот у нас уже есть базис, который...
Well, yes, in some sense, that's exactly how it works. Absolutely. But let us make it a bit more precise. So, so we consider the collection of. Okay, maybe indeed it's a good idea to work out the first example. Try to do this. So before the proof, let's consider an example. So n is 1. So meaning that z minus w to the a 0. I want to conclude this that a is g of w times delta of z minus w. And indeed, since so what do we know? We know that a I j plus 1 minus a plus 1 j equals 0. Yes, for any I and j. So this just by multiplication formula, and therefore, so a is the sum AP from Z, where AP ij is non-zero only if I plus j is P. So this is kind of homogeneous component for our series, because though our relations are homogeneous, where therefore the any solution can be decomposed as a sum of homogeneous components. And well, for also it is clear that the space of AP satisfying our condition is one-dimensional. Okay, and so we do have such a solution. So can you say me what's that? So can we explicitly give the solution for AP?
Ну, AP это в точности вот это вот самое G. Ну,
Andrei, you're muted. Did you say something?
не слышно меня?
No, I can hear you, but it seems that Andrei Grigoriev did say something, but maybe.
I didn't.
Ah, you didn't. I'm sorry. Yes. So, yeah, Sasha, can you say once again?
Ну, я хотел сказать, что вот эти вот AP, они, значит, ну, если в нашем конкретном случае, когда n равно единице, большая часть из них это нулевые. То есть
Yeah, but can you give explicit answer? So AP equals to what?
AP equals to, ну, я думаю, что это какая-то GP от W на D, сейчас, GP минус 1 от W.
No, but you see, G should be some concrete series. So we need just one-dimensional solution.
Ну, давайте попробуем. Такой ряд, значит, Z.
No, G depends on W, right?
Хорошо, да, W. W от A. W в степени K, давайте напишем, не знаю, на AK плюс, AK запятая K плюс P.
No, we don't have any A. Yes, now we just need some very concrete numerical answer. Yeah, so I mean, just a concrete answer.
Сейчас, ну я так понял, что у нас остается еще какая-то свобода. Сейчас, ну в смысле, можно я скажу, как я могу? Я скажу, что это G от W на dp минус 1 от дельта функции.
No, but you see, this is not what we want, because so our capital N is 1. So our sum should range from k equals 0 to 0. So,
Ну вот мне кажется тогда, что в таком при n равном единице именно у нас
so we need just G of W.
Ну, у нас, если p будет больше единицы, то будет 0.
No, for each P, we need one-dimensional solution. So one solution, one non-trivial solution.
Ну, при p равном единице у нас будет решение. Сейчас.
Yes,
Is what is the degree of so we're trying to find the solutions in the homogeneous subspaces, yes?
Absolutely. We need we want a formula for AP.
Okay, then AP is, I think, Z to the I, W to the pi, P minus
but
I.
let's look once again at this formula. Yeah, can you see what I'm now overlining? Yeah. So
yes.
we want A to be.
So so you want to represent it as G of W, and you're asking what is G or what? So now I don't understand the question.
Ну, тоже не очень понимаю, что мы хотим. Мы хотим G через A выразить или что?
Вот я сейчас ничего не слышу.
Я тоже ничего не слышу, и более того, вас не видно.
Why?
Hello.
Yeah, can you hear, see me?
Yes,
Yes.
yes.
Yeah, so let's have a problem with the electricity and everything went out, and also the internet just went out. So let me, so I switched on another source. So let's get back to our discussion. So we were thinking about the example n equals 1, and we want a solution for A, for AP, the pth homogeneous component, and the solution is like in the box here. So
You're asking about the solution in this form, g of w times this delta function.
absolutely.
So g of w, I suppose, will be w to the p plus 1.
Excellent. Absolutely.
Okay.
So any comments, questions, remarks?
Да нет, понятно теперь, да.
Mhm. So what about other students? So do you have any questions why this should be true, or? Okay, so it was actually a good idea to work out this example because so it's turned out to be non-trivial. So let's see how it works. So now let's do the general case. So our n is now an arbitrary number. And so let us denote, so we consider the collection of coefficients A and J, and the operator delta applied to A, which is AI plus 1 minus AIJ, oops, AI plus 1J. And so we know that delta to the n, A is 0. Well, we had this condition for n equals 1 upstairs, and now this is the general n case. Okay, and so this is the condition. Now, so again, before A is decomposed as the sum of AP. And we just need to write a formula for the AP. So we know our equation delta n A0 is of order n, and therefore we have n. So let me put it like that. So the space of solutions is n-dimensional for each p. Yes, so this should work for each p, and therefore we just need to find out n linear independent solutions of this relation. Could you suggest these n solutions?
This is just this is ну, короче, надо взять катую производную от дельта-функции и умножить ее на z в степени p плюс k. На W в степени p плюс k.
So this almost true. So what the suggestion is to take w to p plus k, and then dw to the k, delta z minus w, and k goes from 0 to n minus 1. So this is almost true. So what do we need to fix?
+1 probably.
Yes. So because the delta function, so the sum of the powers of z and w, and delta function is -1, and we take k's derivative, then the sum should be minus k minus 1. We need totally to have p. Okay. So the only point is why these solutions are linearly independent. So any suggestions?
We can multiply it by difference maybe of z minus w to the like to the maximal power, then we obtain coefficient before the maximal power of differentiation, or
So
Probably you should compute some residues.
so these
take any linear combination of these solutions, and then let we have the maximal power of differentiation n. Then we can multiply it by z minus w to the power of n. I'm sorry, I have a delay of pictures, so maybe I don't see what
no, it's okay.
is
Yeah.
written, but you can say if I think something wrong, or
Yes. So and say alpha and -1 is non-zero, then so we conclude that just sorry, I'll be back just in a half a minute. So say if alpha n minus 1 is non-zero, then we can multiply. Okay, so maybe I should say that then z minus w to the n minus 1 of the sum and this equals to, so all the terms are killed, but alpha n minus 1 w to p plus n, and z minus w to the n minus 1, w to the n minus 1 delta. And the only thing to check that this is non-zero it's easy to check. So you see, not only the W satisfy the simple relations, they do provide kind of solutions for our problem. Okay. So
А можно еще другое доказательство сказать, что вот если мы возьмем производную от дельта-функции, то у нас там получится ряд, в котором будут там линейные члены по номеру, ну, если мы посмотрим на дельта-функцию, вот разложим ее в ряд, то там единицы стоят везде. Если мы продифференцируем, там везде будут линейные, ну, там будет как бы линейная функция от номера степени, которую мы смотрим. Если возьмем там вторую производную, то будет уже квадратичная функция. Ну и, соответственно, у нас не может быть никакой там никакой линейной комбинации, чтобы все сократилось из-за того, что там квадратичная, из-за того, что у нас будет как бы, что их пространство, если смотреть конкретную степень, это будет, получается, пространство полиномов там от номера с первыми там n ненулевыми степенями.
okay. Good. So any further questions or comments? Okay, so if not, let's go further. So by the way, is the connection stable now? So you can.
Yes. Все хорошо.
Okay, that's good. Okay, so then so let's consider the delta function again. So function, and then so by the very definition, so this is a series in Z and W, and so let me ask you the question: is it true that delta of Z minus W? Okay, maybe let me do one more step before I proceed. So by definition, W sits inside C of Z plus minus 1, W plus minus 1. So we have both infinitely many negative and positive powers of Z and of W. And now, now let us consider the decomposition. Delta plus. And so what was that? So by definition, sum, so let me not misuse the symbol. So delta plus will denote the non-negative powers of Z, and delta minus is going to denote negative powers of Z. And of course, this second term can be also written as the sum n greater than 0, W to the n Z to minus n minus 1. So you can see that I should write this equals to this and this equals to this, that W delta plus and delta minus are kind of very similar one to another, Well, the only difference is that in delta plus you take non-negative powers of z, and in delta minus you take non-negative powers of w, and they, since in the delta function they sum up to -1, then it's very kind of more or less the same. So now the question I wanted to ask you, so let us consider two rings. This one and so let me ask you one question. So please raise your hand just in Zoom if you think that they are the same. So these two rings are the same. So one hand. Okay, and all other students, they think that they are different. And please raise your hand now if you can give an example of a series sitting in one ring and not sitting in another.
Я могу, только я не сообразил, как нажимать руку.
So if you want to vote, then
Внизу в реакциях там рука есть.
okay. Yes. So only one hand. And what about other people? So I suggest we think for half a minute.
Возможно, можно привести такой пример, когда мы начнем раскрывать и приводить слагаемые в какой-то степени, там получится что-то плохое.
But at least, so can somebody say what's written here? Maybe this is the problem. So can somebody just say in words, what is this object?
Ну, сейчас. Здесь написаны, значит, как бы как это правильно сказать, конечные в отрицательную сторону ряды по W с коэффициентами конечными рядами в отрицательную сторону по Z. Вот, а здесь наоборот.
Exactly. So the first thing is you take Laurent polynomials in W and the coefficients being Laurent polynomials in Z. And the second ring is the ring of Laurent polynomials in Z with coefficients being Laurent polynomials in W. So what about the difference?
Maybe we should take some Laurent series in some just series in Z where coefficients are Laurent polynomials with degree which goes to minus infinity. Like Z to the power of n and W to the power minus n. And this will not be in the second space, probably.
So I claim that we do have an example on the border.
Yes.
So
Excuse me, are those Laurent series or infinite series?
So if we put two round brackets, this is the notation for Laurent series. So let me recall that. In Z. So
Usually they seem to be the same.
say it again.
Intuitively, they seem to be the same.
But let's work out an example. So let me take delta plus. So is it an element in the first ring?
Сейчас, ну вот нет, вот для первого он не является, вроде, если я правильно понял.
So it does not sit here, but it does sit here. Because so it's not a Laurent series in W, because the powers of W go unboundedly to the minus infinity, and it does sit in the Laurent, it is a Laurent polynomial, the Laurent series in Z, because we have only non-negative power sets. And you would take delta minus. So then this guy does not sit here. Sorry. But it does sit here. So any questions?
Ну вот, насколько я понимаю, в смысле, что вот эти вот, ну, вот это вот дельта плюс и дельта минус, это примерно, ну, разложение одного и того же ряда, ну, то есть, это, ну, если их просуммировать в геометрическую прогрессию, то это получится один и тот же ряд. Там 1 на z минус w. Вот, но если смотреть как бы при z меньшем, ну, но один из них получается, если смотреть при z меньшем w, а другой, если смотреть при w меньшем z.
Yes, it's also true. So we'll get to this point a bit later. You're right, absolutely. Okay. So so let me, since this turned out to be a bit problematic, so let me put forward the following remark. If I take C of Z of W, and I intersect it with C of W of Z, can you tell me what's that?
Может быть, можно назвать это C и поставить две, ну, как бы из это W в середине между скобками. Ну, в смысле, что... Ну, в смысле, они, все члены ряда конечных, ну, и по Z, и по W конечные вниз, ну, просто... Здесь это ряды, у которых, ну, как бы, А и G на Z и на WG, где И и G меньше, ну ограниченный.
Можно, наверное, поставить скобки, написать Z запятая W, так?
Ну да, я вот так предлагал.
So these are what? So once again, so this should be series in ZW, formal power series, yes? So we got no restrictions on the positive powers, but as for the negative powers, we have just polynomials in Z inverse and W inverse. Is that fine?
Mm-hmm.
Okay. So in other words, the intersection of these two guys is kind of very concrete one, very concrete thing. So you just take all possible series in Z and W, and in inverses you take polynomials. Okay. Good. So that's it. Now let us get back to the Sasha's remark. So consider 1 over Z minus W, and then let us expand it in two different ways. So one way is to write it 1 over Z Z, and this is some Wn minus n, and this is nothing but delta minus of Z minus W. Okay, and from the other hand, we can write this as minus 1 over W, like this, and so this is minus 1 over W sum 0 and W to minus n, and this is delta plus. Okay, so the conclusion is that delta minus and minus delta plus are expansions of 1 over Z minus W in two different regions. Yeah, one region is Z over W less than 1, another region is W over Z less than 1. Okay, so this is a remark, and now, so we have not too much time left, but nevertheless, let me give you one of the central definitions of our course. So let V be vector space. So then the expression A of Z, which is the sum A J Z to the minus J. A J is endomorphism of V, is said to be a field.
And G are integers or positive integers or what?
Just integers, all possible integers. So this is a series Z in both directions, and J is an arbitrary integer. So this is said to be a field if for any V in V, A of Z V belongs to C of G. So in other words, A J V is 0 for J large enough. Okay. So well, this is some condition, and actually the situation we are going to work with is as follows. So the usually V is graded. So V is the direct sum Vn and Z. So in such a situation, the operator A is said to be homogeneous of degree K if A of Vn sits in Vn plus K. Okay. So why do we care? Because of the following observations. So let me give one more definition first. So a field A of Z is said to be of conformal dimension delta if A of J is homogeneous of degree delta minus J. So let me check. Yes, delta minus J. So for example, delta is 0 is equivalent to saying that A of G has degree, AJ has degree minus J. Okay. So the observation is as follows. So assume that Vn is 0 for n small enough. Yes, it means that our decomposition of V, it has only it has instantly might have instantly many components, homogeneous components, but only finitely many negative ones. So then any field with conformal dimension, so just any field which has any conformal dimension. Well, I would say, so let me put it another way. So just let me say that, and then if delta is the conformal dimension of A of Z, then and V sits in VK, then A J of V sits in where?
Сейчас, ну, in VK плюс
Delta minus J.
Like this, right?
мгм.
So therefore, AJV is 0 for J large enough. Okay. So okay, I'm sorry, I'll be back just in a minute. Okay, so this means that just the condition of being a field is automatic here. Okay, so I think we can stop here, but next time we'll start studying the property of locality. So any questions?
Do we define the conformal dimension only for fields or for any such operators?
For any such operators. Well, I wrote
Because
it,
in the definition you wrote for a field,
you're right.
and
yeah. In principle, we can write it for.
Could you scroll please to the definition of A of Z?
let me maybe even put here.
Upper.
I'm sorry, just another half a minute. Yes, so the question is about this one.
No, could you please scroll to up to the definition of A at Z?
Yes.
Yes, here. We say that A at Z applied to V is in Laurent polynomials, and AG V is 0 for G much
Okay.
more than 0. Why much less than 0 if you have AJ Z minus J?
So first of all, I did a mistake and you did not correct me. So if I apply A of G to V, what do we get? So, oops. So what should be here? So AZ to V.
Здесь вместо C должно стоять эндоморфизм.
Absolutely. Not endomorphism, should be V.
Ой, да. Конечно.
Okay. And now, so AJ of V should be 0 for J large enough, because we want to have only finite the many negative powers of Z. So this, okay. Good. Any further questions? Okay, so if not, I'll stop the screen sharing and see you next week.
Thank you. Goodbye.
Bye-bye.
Thank you.
Thank you, goodbye.
Goodbye.
Thank you.